Hello, everybody. So now we're going to discuss more of our sampling distributions using Excel to make those calculations. So the last week we talked a lot about sampling distributions for a population mean. And let me get that written out. What this amounted to was first of all, we selected a sample size. So we choose a sample size. And the variable we use for that sample size is the letter n. Then we go to our population and we select all possible samples of size n. Now this is done with replacement. So that means that items can be in more than one sample. In fact, by definition, there will be two samples that are the same except for one item being different. We calculate the mean of each sample. And these sample means are the elements of the sampling distribution. And remember, we said the central limit theorem tells us, let me catch up with my writing here. It tells us that the mean of the sample means is exactly equal to the population mean. And by population mean, I mean the mean of the individual values in the population. So this is the mean of the x bars. Mu of the x bars is just equal to mu for the population. And the standard deviation of the sample means sometimes referred to as the standard error of the means, is equal to the population standard deviation divided by the square root of n, the sample size. So the standard deviation of those sample means equals the standard deviation of the population divided by the square root of n. So what does this mean? Well, it means if the population distribution looks like this, a bell curve, then the sampling distribution will have the same mean, same center. It's just going to be narrower. Which makes sense because while individual values, we might be able to select one really small or one really large. If we're selecting a sample, we'd expect that in that sample, if we have one large value, we'll have other small values and they will average out to give us a mean of that sample that's closer to the center of our distribution. In other words, closer to the population mean. And so the example, a similar example might be, let's say we're talking about Wilson's Gym. And at Wilson's Gym, the mean bench press for the competitive athletes will go of the heavyweight lifters is 295 pounds with standard deviation of 45 pounds. So, what is the probability here? Let me write this out. That a randomly selected athlete, we'll say a randomly selected lifter, benches at least 300 pounds. So this is just a single value. This is just a normal probability. So this is a normal distribution. Now, remember, the normal probability in Excel gives you the probability of being less than a value. So it's going to be 1 minus this to get the greater than. This will be the probability that x is greater than or equal to 300. So we have to use that complement. So 1 minus 300 with a mean of 295 and a standard deviation of 45. And of course, we always go with true in the Excel formula for normal probabilities. So let's switch over to Excel here and we'll calculate that. So equals 1 minus norm.dist. The value is 300, the mean is 295, and the standard deviation of 45, and of course true as always. We get 0.4558. We'll go to 3 decimal places. Come on. And this makes sense, because if we're looking at that bell curve, this is an individual value, so it's just the population distribution. The center of that population distribution is 295. This is 300. We're finding this area over here. It's going to be close to half of the distribution because 300 is just barely bigger than the mean. And again, this is a single person, so we don't have to adjust the standard deviation. This is just a pure normal probability. But now for a second problem, let's take a look at what's the probability that a simple random sample of 25 lifters has a mean bench of at least 300 pounds. Now, this is a different story. Now we're taking a sample and we're looking at the mean of that sample. So now we have to use the sampling distribution because we're comparing the mean of a sample. So we're looking at the probability that x bar is greater than or equal to 300. So it's going to be 1 minus because we're looking for greater than again. Norm.dist. Still 300. Now the mean of the sampling distribution is just the same as the population mean, so that's still 295 pounds. But what changes at the sampling distribution is we now have to adjust the standard deviation. The standard deviation of the sampling distribution is the population standard deviation of 45 divided by the square root of the sample size, which is 25. And I use SQRT there instead of the square root symbol because that is the command in Excel for square root. So let's take a look at that one. Equals 1 minus norm.dist, 300, 295. And now you can actually just put in here 45 divided by the square root of 25. Make sure you close that parenthesis, comma, then put in true for cumulative and close the parentheses on the whole command. And now we get 0.2893. That's exactly what we looked at before. We even though 300 is just barely larger than the population mean, now that it's a sample of 25 lifters, and we're looking at the mean of that group, there might be one lifter in the group that has a really large high bench press, and someone has but there's a good chance there's also going to be someone with a fairly low bench press, and the mean, it's going to average out to being closer to the center of that distribution. So it changes that probability drastically. And now for our third question here, what if n is 100? So now it's a simple random sample of 100. And so the only thing that's going to change up here is this 25 is going to now change to 100. So if we go over to Excel here, this is going to equal 1 minus norm.dist, still 300 pounds. 295 is still our mean, but now it's 45 divided by the square root of 100. And we get 0.1333. So as you can see, the larger the sample size gets, the less likely it is that the mean of that sample is going to be further away from the mean of the actual population. So now let's look at a sampling distribution for population proportion. So this is a little bit different because it can only apply to a sample. You cannot have the probability of a single item having a proportion greater than or less than a certain amount, because either that item has the characteristic, so its proportion would be 1 or 100%, or it doesn't have the characteristic, so its proportion would be 0. But it's the same thing. We are selecting a sample size, and we'll call that sample size n again, as always. And once again, we select all possible samples of that size. Now this time we're looking at a qualitative variable. So we're calculating not a mean or a median, we're calculating a proportion. How many of the items in that sample have the desired characteristic divided by the total size of the sample. So we calculate each sample proportion. And the sample proportions now are the elements of the sampling distribution. And so there is a central limit theorem for proportions as well. And it says the mean of the sample proportions is just equal to the population proportion. So it's all of the possible samples. So it's a population mean and the sample proportions are p hats for this textbook, is just equal to p, which is the population proportion. The standard deviation of the sample proportions sometimes called the standard error of the proportions, is equal to the square root of the population proportion times 1 minus the population proportion over n, the sample size. That's all in the square root. So the standard deviation sigma of the p hats of the sample proportion equals the square root of p times 1 minus p over n. Now, because we don't necessarily know the population proportion, we will often use p hat for p. Now, in some of our examples, the example we do today, we're going to have a population proportion. But if we don't, we expect that the sample proportion is going to be reasonably close to it, so it can work in here. This formula is not particularly sensitive to slight changes in p. So let's look at an example. Let's say only 21% of users who start, we'll keep with the workout theme here, at the gym the first week of January. That's all of your New Year's resolution workout people are still active at Valentine's Day. So in other words, by February 14th, many have quit going to the gym. Only 21% are still going to the gym as of February 14th. If a simple random sample of 40 members who started the first week of January is selected, what is the probability that at least 10 are still active at Valentine's Day? So first we need the sample proportion. The sample proportion here is 10 out of 40, or 0.25. So we're saying at least 25%. So what we're finding here is the probability that the proportion p hat is greater than or equal to 0.25. Remember, the population proportion here, p, comes from the 21%, so that's 0.21. So greater than, we're still looking now at a complement, because remember, Excel's normal function does less than. So this is going to be 1 minus norm dist, the 0.25, with a mean of 0.21 and a standard deviation of the square root of 0.21 times 1 minus 0.21, close the parentheses, divided by 40. then of course true, and close that parentheses. So let's go to Excel and type this in. Equals 1 minus norm.dist, oops, 0.25 with a mean of 0.21. The standard deviation of the square root of 0.21 times parentheses 1 minus 0.21. Close that parentheses divided by 40 and close the square root. And then comma true, we get 0.2673 is that probability. So just over 26%, just under 27% probability that we'll keep a quarter of those people still going if the sample size is 40. But what about if the random sample is 100 people? So that would be 25 out of 100. So this is still the probability that the sample proportion is greater than 0.25, because 25 out of 100 is still 25% or 0.25 proportion. What's going to change here is that this is going to become 100. So let's go make this calculation. Equals 1 minus norm.dist, 0.25, with a mean of 0.21. Now this is the square root of 0.21 times parentheses 1 minus 0.21. Everything's exactly the same in our formula so far, but now it's going to be divided by 100 is our sample size. And that probably gets smaller, 0.1630. As we expected, the larger the sample size gets, the less likely it is to have a sample proportion that is significantly larger than the population proportion. Remember, the population proportion was the 0.21. So 25% or 0.25 proportion is significantly larger than that. And let's keep going. What about 75 out of 300? So now again, the only thing that's going to change here is the 300. So this is going to become 300 instead of 40 or 100. So let's do equals 1 minus norm.dist, 0.25 with a population mean of 0.21. And again, the only thing that's going to change here, still 0.21 times 1 minus 0.21 divided by, the only thing that's changing is that now it's 300 instead of out of 100 or out of 40 like we've had in the last couple examples. And now it's 0.0445. This becomes significant because remember we mentioned before that unusual is often a probability of less than or equal to 0.05. So now when the sample size gets probably a little bit less than 300, close to 300, it now becomes statistically unusual for the sample proportion to be 25% or greater, or 0.25 or greater. So even though it's the same sample proportion, because it's a bigger sample, it now becomes an unusual result or a statistically significant result. As we move into the next weeks, this is going to be important because for confidence intervals, we can reduce the size of the margin of error by taking a larger sample, because as the sample gets larger, probability is that the value is going to stay closer to the population mean or the population proportion. Same with hypothesis testing. It's going to be important because you want to get a statistically significant result, which is often looking for an unusual result. Well, taking a bigger sample makes it more likely that your result will be deemed unusual. So that is the sampling distribution for means and proportions using Excel. If you have any questions, please let me know. Otherwise, we'll see you in class.